Okay, so now we have a problem involving the calculation of enthalpy changes by using bond enthalpies. And the specific reaction we're looking at is the decomposition of ethylamine, C2H5NH2, to produce ethene, that's C2H4, and ammonia, NH3. And we have to use the bond enthalpy data that we're given to calculate an approximate value of the enthalpy change for that reaction. Okay, so that's what we have to do, and the process that we're going to follow is the following. We are first of all going to write down our reaction in terms of the compounds that are involved. So we've got C2H5NH2, which undergoes a reaction to produce C2H4 and NH3. Okay, that's the reaction that takes place. Now, what we want to do is to work out which bonds are broken and which bonds are made during this chemical reaction. So the first thing to do is to draw a display structure for the reactant. Where we put in all of the bonds associated with all of the atoms, and also for the products. So we're going to draw a display structure for ethene as well, which looks like that, and a display structure for ammonia, which we should draw like that. Okay, and the next thing we need to do is to list all the bonds that are present. So for the reactants, you can see that we have one carbon-carbon bond. We have 5 carbon-hydrogen bonds. We have one carbon-nitrogen bond, and we have 2 nitrogen-hydrogen bonds. Okay. Altogether, on the product side, we have one carbon-carbon double bond. We have 4 carbon-hydrogen bonds. We have 3 nitrogen-hydrogen bonds. Okay. So, how are we going to simplify this? We don't need to consider all of these bonds because quite clearly we have some bonds that are similar on both sides of this reaction. So what are we going to do about that? Well, clearly the carbon-carbon single bond is only on the reactant side, the carbon-carbon double bond is only on the product side, but we have carbon-hydrogen bonds. We have 5 of them on the reactant side and 4 of them on the product side. So if we look at the numbers, 5 on this side and 4 on that side, we can effectively discount those 4, take them away to leave us with one carbon-hydrogen bond, one net carbon-hydrogen bond. So if we're looking at the net bonds, we've got the carbon-carbon, we've got one carbon-hydrogen bond that's broken, we've then got the carbon-nitrogen bond, and then if we're looking at the nitrogen-hydrogen bonds, we've got 2 on this side, 3 on that side, which is a net of 1 on this side. So the net bonds on this side are the carbon-carbon bond and 1 nitrogen-hydrogen bond. Okay, so of all the bonds, the only bonds that we need to worry about are these 3, which are broken on this side, and these 2, which are made on the product side. Okay, so we're going to summarize that information. We're going to consider all of the bonds that are broken first of all. The net broken bonds that we have to consider. Remember, we had a carbon-carbon bond, we had a carbon-hydrogen bond, and we had a carbon-nitrogen bond. And the energy changes associated with these are 346 413 and 305. So the total energy that we have to put in to break those three bonds is the sum of these three numbers, which is 1064 kilojoules in this case. That's the amount of energy that we have to put in to break those bonds. Now let's consider the bonds that are made. The bonds that are made, we had a carbon-carbon double bond and a nitrogen-hydrogen bond, the energies of which were 602 kilojoules for the carbon-carbon double bond and 391 for the nitrogen-hydrogen bond. Okay, add those two together, gives us 993 kilojoules are produced when those two bonds are made. So the energy of reaction, or the enthalpy of reaction, is the difference between those two numbers. Okay, the energy that we put in is positive, so we write that as a positive number, and the energy that we get out when the bonds are made is a negative number. So we put a negative sign in front of the energy of the bonds that are made. We then work out the result here, which gives us 71 kilojoules as our enthalpy change for this reaction as written.